wanted to look at this line paper, and I wanted to do a deep dive into it, but I didn't manage to get that far. So I'm going to give you sort of a, it's somewhere between a deep dive and an executive summary. But I did find somebody who made a PowerPoint that that's also pretty nice. So I might jump to that in the middle of this presentation. Okay. So the paper that I want to talk about is called. Well, here's an overview. I'm gonna introduce this line paper. I'm gonna give an executive summary and talk about the core ideas and what are the main achievements of this paper. What does the AI community think about it? And then I'll just point out some future research ideas that were suggested by the authors. That was back in 2016, and I haven't followed up to see if they've actually been done. And then a number of possible applications also listed in 2016 by the authors at the end of the paper. And then at the end, I'll provide a link to the implementation code that the authors made, and then we can talk. Then people can discuss and ask questions. So with that, I'll go to the first slide. Can everybody see this slide?
Yes.
Okay, great. So the paper is called "Why Should I Trust You? Explaining the Predictions of Any Classifier." It's kind of a very it's a big claim. I mean, and it's like the paper doesn't actually do that, but they give you a method for doing it, and then they apply it to some simple problems. The authors are Tulio Ribeiro, Samir Singh, and Carlos Weston. The paper's on archive, and here's the link. And there's a couple of references that I'm going to come back to during this talk, because I think they've done some nice. There's some nice information on them that we can look at. In particular, I looked up to understand what the AI community thinks of the paper. I looked it up on Semantic Scholar, and it has some nice information there. We'll go to that page a little later. Also, O'Reilly Press. The authors made a short explainer that they published on O'Reilly Press, and we might. It has some nice graphics in it, so I might go to that during the talk too. And then I found also a nice overview of the paper at sort of the level that I was aiming for, but didn't have time to do. And it's by this probably a Stanford undergrad, and I think I'm going to go to that also during this presentation to help. All right, so the first thing is an executive summary. What I think is that LIME is a framework for exploring the trustworthiness of a model. And again, trustworthiness is a very qualitative thing, but they try to make it quantitative. Trustworthiness is like, you have a model that has 97% accuracy, and you're all pumped about it, but the thing is, this model, as we're going to see a little later, this model might be a load of crap. And this method gives you some ways to probe that and see if the model is actually doing what you think it's doing. They claim that that the framework that they present is potentially applicable to any model, whether it's a neural network model or a support vector machines model or a random forest model, or any type of model at all. In principle, one could come up with a line, one could apply this technique to that model, but they don't actually do that. They do it for a few simple models. And as I was saying, the holdout accuracy, if you go by that, you could really be fooled sometimes. And there's a couple of really interesting examples that we'll come back to make this point. So you might think you have a really highly accurate model, and you might think it's all great, but then you find out that, well, it's not really doing what you think it's going to do. All right, so that's the executive summary. The core ideas to make this to apply this framework. they transform the features into what they call interpretable representations. So in the two simple examples they do are a text model where they're doing classification of some news groups as to whether they're atheist or Christian. And the second example they look at is classifying images. So if it's a text model, what they do is the features are, instead of the word vectors or whatever that you usually use in a natural language processing model, they use they transform the features into simpler things like the presence or the absence of a word. As for the images, they sort of boil down the image into a bunch of superpixel areas that are of similar colors. So it's a simplification of the features. Next, they introduce a complexity measure because they're trying to make something explainable, and the idea is that the explanation should be simple, and so that is, the model should be simple in order to be able to explain it. So the more complex the model, that they introduce this complexity measure that sort of represents how complex the model is. So if it's a random forest model, it could be the depth of the trees, or if it's a neural network model, it could be the number of non-zero weights that measures the complexity. Then they
excuse me.
Yes.
I thought it was in weights.
Sorry, let me
For ReLU,
turn up my audio so I can hear you better.
for ReLU, I thought it was negative numbers, so that zeros were okay. Or I'm misapplying this.
Okay, well, I'm not exactly sure the details of the implementation, but it could be the number of weights that are larger than some number, then, if it's not necessarily non-zero. The number of, the number of significant weights that you want to consider.
Okay. Okay.
Then they construct a loss function that, okay, so they have a way of going from these simpler representations to a local linear model. So no matter what your model is, whether it's a neural network model or whether it's support vector machines or whether it's a logistic regression, whatever, they go to this sparse local linear model around a given example. And they invent this loss function that measures the disparity between the actual model that you're using and this approximate local linear model that you're using. And then they, to get the explanation, the numbers that they use for the explanation, they minimize the sum of this loss function of this localized loss function and the complexity. So they're trying to minimize two things at the same time. They want to make the local model as close as possible to the actual model, but also they want to minimize complexity as well, complexity by this measure that you've introduced. Okay, so that's about as deep as the dive is going to be here. So the key achievements of the model is that it helps you to gain insight into your model predictions. You can actually look at any given prediction and see why the model made that prediction, what things it considered, and we'll look at that for a couple of simple models later on. It gives you a way to assess whether the model is trustworthy or not. You can check thousands of, if you have lots of data points, you can go and check thousands of data points and you still won't, maybe if you're just checking the data points at random, you may not, it would be very, very time consuming. So they've introduced this algorithm that helps you to select any given number of examples. Suppose you say that you have time to look at, a dozen examples. So they have an algorithm that will then select 12 examples that are the most disparate possible, that span the whole data set as much as possible. So it's a representative set of examples. So, given the time that you have available, their algorithm will help you to select a reasonable set of examples to examine. to examine these predictions. So when you do this, you will either you'll either have a basis for trusting the model once you see that all of these different types of examples are the explanation that line comes up with makes sense, and then you'll have more trust. This is a way of building trust in your model and helping your users to build trust in the model when you show them this. But it can also point out examples where your predictions are way off, and it can help you to say, oh, well, I've got to do a little bit of feature engineering, or I've got to change my model a little bit, or change my, or yeah, maybe do some feature engineering to in order that I can get a better result. And we'll see that again in a couple of slides further. So the bottom line is it gives you a way to explore the trustworthiness of your model and help you to make the model better if you find that it's not trustworthy. All right. So what does the AI community think? I want to go to this Semantic Scholar abstract and show you. I think I'll just pull it. Let's see.
So
Yeah.
one quick question with regard to the trustworthiness of the model.
Yes.
Is it when we say trustworthiness, is it would it tell us that it's overfitting, underfitting, or there is a data leakage? How would we?
Yes, it can help you to see whether there's data. Sometimes you'll see that there's data leakage. Sometimes you'll see that you're fitting to the wrong thing. You know, you're fitting. Yeah, it could be overfitting. And there's some nice examples that I want to get to that will show this to answer your question in more.
Okay. Okay.
So I want to go to this page. Thank you. I'm going to get rid of this one though. And bring this one up. And, can people see this?
No, actually,
Okay.
I think
Okay. Oh wait, it's logged onto my presentation. Now I gotta get it to lock onto something else.
yeah.
No, just share your desktop, or there's the option to either share your desktop or screen, and that will.
Like new share, when it says new share, is that what it is?
Yeah, well, I think just unshare and then share again, and when it call for a share your desktop instead of just one screen.
Okay,
Then-
I'm gonna say stop share, and then I'm going to do the share again. And then I'm gonna pick the screen that I want to share. I think it's this one. Yes, thank you. Yeah, so can people see this?
Yeah.
Okay, this is the Semantic Scholar. It's on, if you go to the link on archive, this is something you can click on. So I clicked on it, and it shows you some interesting stuff. It shows that it's highly influential, that it's influenced 111 papers, and then you can actually look at some of the papers that it influenced, and then it also shows that it was highly cited. It has over 1,500 citations, and you can look at the citations, and then you can also look at the citations and some of the related discussions. So I wanted to be able to scroll. I think I can scroll. Can people see when I'm scrolling?
Yeah.
Okay, great. So it gets me to, this is how I found this nice presentation. These presentation slides are what I want to visit. I think I want to visit these next. But so this is from a Stanford student, and I'm going to go there. So this guy's name is Yuan Liu, and he goes by Lucas, and he has some nice slides to explain the paper. He used some of the graphics from the paper, so he did a lot of this work that I didn't have time to do, and that's why I'm sort of leveraging that. So here's a doctor who's trying to figure out if somebody has the flu, and he or she collects a bunch of data, and then this machine learning thing. This machine learning model makes the classification whether it's flu or not flu. So the Lyme model identifies which of these features are causing it, are having the most weight in making its decision. So the model has decided apparently that this is say some neural network model or any kind of model. It decides that the patient has the flu, and line says that the reason behind its decision is because the patient was sneezing and had a headache. But those are the things that would mitigate for the flu, that would sort of say the patient has the flu. But then also no fatigue. The patient, normally when somebody has the flu, they would have fatigue. But the model decided on flu anyway because I guess it found a preponderance of symptoms that were in favor of the flu. So then, a doctor could look at this and say, well, the model says it's the flu, but I don't think it's the flu because in my experience, if there's no fatigue, then there's no flu. So that's the way that this, the lines can help somebody to decide whether or not to trust the model. All right, so here's the thing about the 20 subsets, the atheism versus Christianity news groups. And so you train it on these 20 news groups. You ask it to predict, and you have two different models. One of them has an accuracy of 89%.
What's the network limit to this determine? Which part of this house can't you make use of it?
I'm sorry.
Joseph,
Yeah.
Joseph, you have the option to just mute everyone, so just do that, and then anyone who has a question can unmute themselves later.
I used to walk inside the room before, but
Hello. I think people have to mute themselves if there's background noise.
No, Joseph, I suggest you mute everyone. You can do that as the presenter, and then if anyone has a question, they can unmute themselves.
Okay. Let's see. So how do you mute everyone then? Mute. No, that's me.
It says mute all or something like that. Yeah.
I see a mute, but I don't want to mute myself. Manage participants.
Is it? Can you click on that arrow on the mute? Does it show you mute all?
I click on manage participants and then I can say mute all. So I'm going to
do that.
All right, thanks.
Yeah. Okay, so now that way there won't be background. All right, now hopefully I'm not muted, right? So, okay, so if anybody wants to interrupt me, they can. Anyway, so there's this 20 news groups, MA, and somebody built a model. They built several models to decide whether they're atheist or Christian news groups. And one model said it has 94% accuracy, and the other model says it has 89% accuracy. I'm not sure what this next slide is, but this is the slide that was in the paper, showing that on the basis of which these two models made their decisions, show that that the decisions were not necessarily made by in the best possible way. So, these the purple lines indicate the strengths of the words in the news group in the news group post that helps it decide that it's atheist, and the green ones decide this are the strengths of the words that help it decide that it's Christian. Both of these models decided on atheism, but notice this one at the right. It looks like it's deciding on the basis of headers of text in the header, and this model on the left is deciding on the basis of somebody's name or something like that. So when you look at this example, you say, well, my model might not be doing what I think it should do. And then this could help you to change the model. Maybe you want to eliminate the headers from just look at the body text and not look at the headers, and maybe not look at the names, maybe not look at proper names too, because it's making a decision on the basis of proper names too. So in this way, you've noticed that your model isn't as trustworthy as you think, even though it might have a high accuracy. And then you can take steps to change it and make it more trustworthy.
So in terms of, can you go back to your slide, please? So in terms of algorithm 1 and algorithm 2, so we are saying the algorithm 1 has made a decision based on the header, but algorithm 2 didn't.
Apparently, algorithm 2 made the decision based on the header, because notice that all these words, they're not from the body. They don't look like they're from the body of the text. They look like they're from this header.
Posting.
Yeah. So, yeah, and then this one is making a decision on the basis of this word, or partly on the basis of this word, Koresh, and capital God. Maybe that's something that they do find in that people that are atheists tend to use all caps when they say God. I don't know.
Right. Okay. Interesting.
So it helps you to see how, on what basis the decision was made, and then that can give you some feedback. You can go back and change your model, make it better.
Mm-hmm.
So these are the benefits. You can. Here's a sort of an example that's maybe easier to follow and understand. You've got this image classifying model trained on Google's Inception model, and then you give it this image, and then you ask it to classify what the image is. And so it comes back and says it's 32% probability of being an electric guitar, 24% probability of being an acoustic guitar, and 21% probability of being a dog. So then you use line to ask it to explain how it made its decision. And what you see is that it has divided the image up into superpixels, and it's identified those superpixels that were the most important in making the classification. So electric guitar, you notice that it's focusing on the fret and the hand. And the guitar classification is focusing a lot on the body of the guitar. And the dog classification, well, it's focusing on the dog's face at the top. So this tells you this model is at least making some sense, that it's doing what I expected it should do. And given that there are, given that it's easy to confuse electric and acoustic guitar, it's not terrible that it actually had its highest probability for the electric guitar. But at least you understand what the model is thinking when it makes its decision. Here's another one that's interesting. Classifying a wolf versus a husky, and apparently they came up with this model that was incredibly good. It only made one mistake, and so now you're going to go and ask, how did it make these classifications? And it turns out that it's classifying wolf whenever it sees snow in the background. Apparently, I mean, it's all the pictures with wolves are taken in the wild and they have snow in them, and this model is apparently basing a large part of its decision on the presence of snow. So I don't know what you can do to fix it, but at least you know why it's what it's doing. It's any picture that has snow in it might get classified as a husky. I mean, as a wolf, even if it doesn't have a dog in it. In fact, that's what happened. I think there were okay. So
So Joseph, just a quick question.
Sure.
So what's really great about this line model is it's telling you why it's made those decisions, right? So for example, in the husky instance, it's because of the snow. In the other one, it's telling you because it's seen these different components. How is it able to give you that view of interpretability? What is it about this line framework that allows you to do that?
You mean in the it's dividing, okay, at a high level, it's dividing the picture into superpixels that are, so it's simplifying the picture into instead of looking at all the pixels, it's looking at superpixels that have similar coloring. And then it's trying to go to a local model, and then it samples this local model around the picture that you give it, and then it comes up with sort of weights of all the superpixels, and the ones that help it to make its decision the most are the ones that show up in this image to the right. So here's the original image, this wolf. It predicts a wolf, but the superpixels that are guiding its prediction are shown here. They're basically the snow. And here's another one, a wolf this wolf that's growling at you. But to make its decision, it mainly considered this patch of snow to the left. And that's what Lime is doing. It's simplifying the picture into these superpixels of similar coloring, and trying to sample a local model and make a decision based on those superpixels. They also introduced this thing called SP-Line, which is what I was alluding to before, where it automatically selects for you a set of examples that are designed to span the space of examples given the time that you have available. So like, for example, you say, I have time to look at a dozen images. It will find a dozen images with the most diverse explanations and show them to you. So that in that way you can catch, you have a better chance of catching something that isn't really a good explanation. And also you have a better chance of seeing if all of these examples that it picked are well explained by Lime. So here's the thing that this is from the paper. It's the blue and red boundaries show this complex model that you have that you're using to explain your data. And then here's the particular example that you want to explain, this big red cross. And so what Lime does is it builds a local model and samples your space, samples the feature space all around this particular model. All around this particular example. And then it finds the features that were most that had the most influence in making the decision. Not the real features, but the features in this simplified feature space, which in the case of images is the superpixels. And then so look, near this model there's this local decision boundary, but it's not global. It only works near this. It's not necessarily global. It only works near this particular example. All right. So here's sort of a schematic of how back to the dog image on the guitar. It divides the image up into these superpixels, and I'm not sure how it does that. That's deeper than I actually had to go. But I think what you tell it is you tell it how many superpixels you want, and then it will find the say if you say I want 25 superpixels, it will find 25 superpixels that are as close as possible the same color in each one. I'm not sure what the algorithm that it uses to do that is. So again, this is what we went through. This is the second model, which is they call it submodular. They introduce a lot of weird terminology in this thing, but the second model is the SP-Line, is submodular function optimization. That's where they have an algorithm that picks the right number of examples for you to look at, given the time that you have available. So if you say you have time to look at 100 examples, it will pick the 100 examples that are the most representative of that have the most disparate explanations. So the algorithm avoids redundant explanations. It avoids examples that have similar explanations and tries to find examples that have widely varying explanations. And when I say explanation, I mean, for example, in an image, like which superpixels that it's focusing on, that it's focusing its attention on. So that's the end of this little presentation. I'm going to stop this share and go back to the PowerPoint. I can find it.
Sorry, so just another question on that, Joseph. So with the images and so on, where we're able to distinguish between the like the wolf and the husky, for example, yeah. Right? That classification was actually done by, I can't remember, it was either ResNet 100 or whatever. It doesn't matter.
Inception, yeah, Inception.
Okay, fine. It was done by Inception, right?
Yeah. So
the classification was done by Inception, where and Lime is using these superpixels, right? So yeah. Why? Clearly, that classification is actually done by ResNet. So why would the superpixel be a means of explaining why the wolf was picked versus the husky?
It's because in this local model, where you're just looking at the superpixels, it sampled this local model, and I'm not sure when it says sampling, I'm not sure how it's sampling, but it's sampled locally around this particular example, this one picture that you gave it, and it found which superpixels were in this local linear model, which superpixels were having the most influence on the decision, and it reported those. So it maps the inception model to a simpler model that it's dealing with, that it's, this local, they call it this local sparse linear model that's just based on the superpixels.
Okay, thank you.
Yeah, I'm sorry, that's not a deep enough explanation, I know, because I just didn't have time to go into it that deeply. Okay, I'm going to go back to go back to this PowerPoint briefly. Remind myself what I wanted to do. All right, so we've been to the. Oops, I'm going to do this. Okay. Okay, so it went somehow. Yeah, I'm just so in the authors at the end they point to some future research that they'd like to do, and this was 2016, so I'm not sure how much of this has been done by now, but they say that can everybody see this, by the way? Can people see my screen right now?
Yes.
Okay, great. Yeah, so they right now their explanation family, quote unquote, is this local sparse linear model that I've alluded to. They want to be able to extend this to have other families of explanations instead of local linear models. They might want to use decision trees. They seem to think that's a thing that they want to do. So I'm not sure if they've accomplished that yet.
I think in the machine learning course, Jeremy mentioned that it is a wrong belief to use linear models to compute the feature importance. And he, in fact, showcased the trees version of finding feature importance and visualizing those.
Okay. Okay, that was in Jeremy's class?
Yeah, in the machine learning class.
Oh, okay, great. I'll have to go back and look at that.
And even for this convolutional neural network parts, on Twitter, I've seen him advocating about visualizing gradients of the network.
Yeah, I remember that paper. I remember he showed that. So apparently, that was a big paper that was, I think it was shown in 2017. It was really had a lot of attention. And I forget the author of that paper, where he showed how the convolutional neural network, what it's really paying attention to in the image whenever it's making classification. So yeah, so that must be some progress since this paper. He thought it was he had implemented this I guess SP line where he had implemented that for text models in his paper. This guy, these authors, they implemented it for text models, but they hadn't implemented it for image data. They didn't have a way of choosing which images you should look at if you want to get a global assessment of this model. And so maybe there's been some progress on that. I'm not sure. They wanted to explore the theoretical properties, that is the optimal number of samples to look at if you want to assess the trustworthiness of a model. I'm not sure what progress they made on that. And then finally, they wanted to do computational optimization using GPU and parallel processing, because the examples that they showed actually didn't process that quickly. The text model, I guess that did process fairly quickly, but for the inception model, it took something like 25 minutes to process one image. So you can imagine that if you want to do 10 images, that's a significant investment of time if you want to look at a random 10 images and try to see how trustworthy the model is. 25 minutes per image is a lot. So they wanted to speed it up. And their goal is to have something that can give you something in real time, that gives you an accurate and real-time explanation. You don't have to wait 25 minutes. You can get it in a few seconds, like they can with their simple text model. So I'm not sure what progress they made there. They wanted to explore possible applications in speech and video, medical domain for diagnosis and so on, and also for recommendation systems. And I haven't followed up to see what's been done in those areas. So that's basically all I have. And let's see, I put some links here I'm going to share this presentation once I figure out how to do it. I'll share it on Slack or on Fast.ai, one or the other. I put some links on here, a link to the paper, a link to the Semantic Scholar abstract, a link to a brief intro that the authors wrote and it's published on the O'Reilly website, and then this little presentation that I used by the Stanford student. And also, I think at the end of this, I give a link to the Lime code on GitHub so that people could play with it. I haven't actually done that yet, so but I would like to. And that's all I have.
Nice work. Thank you.
Thank you very much, Joseph. I think it was, as always, very interesting.
Yeah.
Yeah,
So,
thank you very much.
Yeah, so I guess we have another meeting next week. And I don't know, I don't know who's presenting for that one yet. But we can talk about possible topics or whoever's going to present.
I have a further question, Joseph. I don't know how far what is the current status of technology, but it would be kind of nice when I think of explainability of machine learning algorithms and let's say AI algorithms and so on. Let's say you're a radiologist and you have some nice recommender system and you run it over your x-rays, your radiographs, and it says lung cancer. Now, as a human radiologist, you would actually kind of enjoy when the model then could actually, when you could interact in the model in a sense, in like the same sense you would interact with a human expert. Like you could ask it, okay, lung cancer, but why is it lung cancer? And then the model would tell you, okay, look here in this picture at the rightmost corner, there is this lesion. I don't know. That's why I decided that it's lung cancer. I mean, have you looked into how far these kind of applications are already, or am I just now thinking basically science fiction?
No, I mean that is actually one of the things that the authors envisioned for this to be used by doctors to help them to trust these predictions. And you can imagine that the Lime, if it's using these superpixels, it could focus on this blob that you were talking about in the upper right-hand corner that shows a lesion, and the doctor could then look at that and decide whether it makes sense. What I think is that in medical diagnosis, you probably AI can't make the final decision. They have to pass on. They sort of make the easiest decisions and then pass it on to the doctor or the expert for the more for the more fine-tuned decisions that have to be made.
Okay,
so,
cool.
In my mind, a model can do like 90% of the work, and then the doctor has to do the last 10%.
Also, what I've been wondering about, let's say if you run a random forest model, it would be kind of nice if the model could sort of give you a logical explanation for why. Let's stick with the medical diagnosis example, and the model could give you sort of like a logical sentence how it came to the conclusion that this patient has, I don't know, fever or whatever, and it says, okay, the temperature is above I don't know, 37.5 degrees Celsius, and the patient has headache. Therefore, I decide that the patient has a cough or fever or whatever. Is that, or am I totally off here now?
No, I think you're right. I think that there is There's this, I think we've seen it in Jeremy's class, it's called Tree Explainer.
Yeah, okay.
And it actually does that. It actually, you know, you pick an example that you want explained, and then it shows the tree that reached the decision. But the problem with something like a medical diagnosis is that the tree is really complex, and there might be, you know, hundreds or even thousands of features that were taken into account when the decision was made. And so the explainability factor is gone. You know, you can't, no human being could look at a tree diagram like that and say, oh yes, I understand that.
Okay.
So they're looking to have a less complex model that gives you something that you can see visually, that you can quickly look at and say, yes, I think I believe that.
Okay.
So that's why they map the features into these simpler things, like instead of a word vector, which is a vector in some multidimensional space, they give simply the presence or absence of the word. This word was or was not in the document, and that's their mapping of the complex feature to a more explainable feature. And they map the complicated image into these superpixels, you know, for the image explanation. Yeah.
Okay, I see.
Anybody else?
Regarding the tree visualization, I've pinned a link of explain.ai in the chat. So it's a book that Terence Parr and Jeremy are writing. So yeah, it also has the details about the tree visualization library that they have created.
Oh, excellent.
Yeah, thank you very much.
And other than that, for the radiology image part, I think gradient visualization technology is already being used for diagnosis. And one of the Fast.ai alumni, Alexander Kadrin, I don't know if I'm pronouncing the name correctly. He recently won the RSNA pneumonia detection challenge using Fast.ai, and he's doing great in that.
Oh, is that on Kaggle, or is that on Kaggle, or is that somewhere else? The challenge?
Yeah, I guess it was. I think so. It was on Kaggle.
Mm-hmm. Okay, well that's all.
I'm picking the name. I think this guy.
Yeah, the guy that Jeremy's working with is Sebastian
Terence Parr.
Oh,
Terence Parr on the book. Sebastian Ruder, he works with on the NLP part.
I see.
And ULM Fit and all is developed with Sebastian.
Right. Okay, thanks. We'll have to look up these things.
I was just going to offer that, you know, another way to check if you should trust a model is using, you know, the precision and recall metrics, you know, for true positives and false positives. And it seems like, I don't know if that's really addressed by this technique.
Well, you're right. This technique is meant to be in addition to that. So, you know, you look at your, you know, they talk about holdout validation. You know, this is something like cross-validation or holding out a test set and validating on the test set, and then you find your accuracy and you know, your recall and precision. But they actually showed that, as you saw, in some cases you can have really high accuracy, but your model is making its decisions for the wrong reasons. Like, you know, like the wolf example that we showed, that it was deciding that things, we saw that the model, Lime showed us that the model was deciding something is a wolf on the basis of having a patch of snow in the picture. So that you could fool the model by showing it some snowy scene, and then it would presumably try to classify it as a wolf. Yeah, that would point to something in your model that needs to be fixed. You know,
point to something in the training data that needs to be fixed in the representation.
Yes, excellent. That's right. That's right. So all your training data has snow in it, and when there's a wolf, and you need to get more training data with wolves that don't have snow around them. Wolves at the zoo or something like that. Yeah. Yeah, so this is meant to be used in addition to that, you know, to those statistics that you're already going to do, you know, you're already going to look at confusion matrix. You're already going to look at accuracy and precision. This is in addition to that.
Yeah, it was a great presentation. Thank you much.
Thank you. Let's see. There's some chat. Let me just quickly look at the chat and see if there's anything that we should bring up. Okay. So people are throwing out some names to look up and some presentations to look at. So this is all worth following up. So H2O is selling their own solution for model interpretability. There's other things that have been done too. I haven't had a chance to look into them. The SHAP thing that Jeremy, I think Jeremy said something about that in the machine learning class. SHAP is for tree models. It's helping to decide to assess the trustworthiness of the tree model. So it's not as general as this line thing is. And then these guys who wrote the line model also came up this year, I think it was last year, with a new model called Anchor. And I haven't had a chance to look at that one yet, but that might be something that's the next step after line. I think that there was Sam had a TWiML meetup where this woman from Germany, I forget her name right now, she gave an overview of this problem of interpretability and trustworthiness, and she mentioned Lime and
Joseph, just to interrupt, I think her name is Shirin Glander.
That's
Shirin
correct.
Glander.
Yeah, that's right. And she talked about Anchor and in her presentation a lot. So,
yes.
So these are things that I plan to explore a little bit more in the future because I'm really interested in this, especially with the the European Union's guidelines that they want people to follow, which make a lot of sense. I think there's an acronym about what you're looking for.
GDPR.
Pardon?
GDPR.
GDPR.
Yeah, GDPR is the name of this European Union sort of manifesto on model explainability and so on. And the idea is that anybody whose life have been affected by the decision of some model, let's say by giving you a loan or letting you admitting you to a school or something like that, or admitting you to a program or giving you a job, machine learning is having an increasing role in all of these decisions, and people are demanding to know, well, how can I trust this model, and why do you think this? Why did the model do this, and why did I not get picked, or why did this person get picked and I didn't get picked? Why didn't I get this loan? And the idea is that the institution that's making the loans should be able to answer that question, and that's what they're asking for. I'm not sure how practical it is that everybody's going to be able to do that, but that's what people are trying for.
Do you mind if I just offer a quick tidbit?
Go ahead.
I was just browsing. Yuri shared a slide share from H2O with their technique for interpretability, and it's in the comments. And if you look at that presentation, slide 13 has an interesting summary of the Lime method, which I thought is relevant to this discussion. And specifically, it mentions that Lime fails, particularly in the presence of extreme nonlinearity or high degree interactions. So I just thought that was an important point as far as the limitations of the Lime method. Yeah,
that's great, and I think that's why the authors are wanting to extend it to tree methods, because their method, their sort of space that they're mapping the model, the complex model gets mapped onto this simple sparse linear model space. And you're right. I mean, if the model is extremely nonlinear, and this linear space is only going to be valid locally and may not be even valid locally. So that's why the authors, I think, are trying to extend it to tree-based methods, and because tree-based methods can handle nonlinearity much better than linear models can, of course. That's a really good point. And so someone said that Jeremy has extended it to tree-based models in in the machine learning class, so that's worth looking at, I guess. Unless maybe that's what maybe he was talking about SHAP. Is that possible? Yeah. I forget. Okay, I think it's Aleph thoughts. You mentioned that Jeremy talked about something in the machine learning model, in the machine learning class that had to do with model explainability. And I think I remember that, and I think it was SHAP that he discussed.
It was tree visualization. I think SHAP was not discussed in the class. SHAP is also a good method, but it was tree visualization basically.
Okay.
On the library that they have developed.
Okay, but was it an extension of Lime, do you remember, or was it just a new technique?
It was a new technique. In fact, Lime was criticized. I remember Jeremy said that like bad ideas die in research, one funeral at a time or something like that. So
that is true.
Linearity is a bad idea which is pretty prevalent. He said, but he was suggesting tree-based methods are better, even for linear solutions.
I see. Interesting. So you're saying that Lime is already obsolete, or is that the idea?
Yeah, I guess so. I think tree visualization is the way to go for structured data, and gradient visualization for image data. And the categoric for NLP, he showed the categorical embeddings visualization. Also, like that German retail chain use case that he had shown, that was visualizing the words, and the whole map of Germany was created by visualizing the location of stores. Something like
okay.
that.
I sort of remember that. I sort of went through that once. Okay, so that's worth going back to. Thank you. All right, I think that'll do it. We're at the top of the hour. So thanks everyone for bearing with, and I'll see you guys next week then.